welcome on how I'm going to lead the Department of Seminar series. I met Angel while I was postdocing at the University of Washington. He graduated in 2016 from the UW Atmospheric Science program and quickly ascended to assistant professor position after a postdoc at GFDL in the Department of Climate and Space Science at the University of Michigan. And he's since moved this summer to the Department of Atmospheric and Oceanic Sciences at the University of Wisconsin. He has many accolades, including the 2018 Holton Award from AGU, and as a Kavli Fellow of the National Academy of Sciences, and in my view, notorious for publishing textbook-worthy figures summarizing the latest breakthroughs in tropical dynamics. So thanks for a really interesting seminar title, and to take it away, Angel, welcome again.
Thank you, Mike. It's a great pleasure to be here talking to all of you today. I've already had multiple meetings, and a lot of these meetings have been really excellent, and I've gotten a lot of information, a lot of good feedback from all of you. So I'm really excited to be talking to you guys today. And the purpose of this talk is to give an overview of some of the recent advances in tropical atmospheric dynamics. I'll just skip the first slide, and out of fear of like screwing up, I'm not going back to the title slide. So this is like the second slide. This is the stuff that happens when you're doing a remote seminar, and you're not exactly sure why things happen, but sometimes things work, sometimes they don't work. So let's just things are working right now, so let's just leave them as they are. So the goal of this talk is, like I mentioned earlier, is to convince you that the recent advances in the tropics have been pretty outstanding. And so we've had numerous great advances, especially in the last couple of decades. And maybe we're really getting to a deep understanding, to the point that maybe we can start writing textbooks about tropical dynamics and tropical meteorology. So I'm going to quickly mention that most of this talk will be summarizing research that I and my research group have done, along with collaborations. But I do want to emphasize that these advancements in our understanding of the tropics have been the work of dozens of scientists, like a great number of people that have done great advancements to our field. And I should acknowledge that this is the work of a community, a big community. And if I were to acknowledge everybody, we'd be talking for numerous days. I'm going to be emphasizing my work, but please do know that this is due. These advancements have been due to a lot of people that have done some really fundamental contributions. So what I'm going to start doing today, before I go and just give you an overview of what's going on in the tropics, I want to give you a historical overview, because I deeply care about this, and I think it gives you some context as to where our current understanding of tropical atmospheric dynamics is relative to the dynamics of the mid-latitudes. So in terms of serious research into atmospheric science, you can argue that perhaps the first really serious attempts of working started in the early 20th century with work like the Norwegian cyclone model. So a lot of this early work in meteorology, atmospheric science in general, started basically in the United States and Europe, Canada, and all these countries in the northern mid-latitudes. And these efforts really did take off somewhere in the early 20th century. And like I said earlier, these started in mid-latitude countries. So as an extension, the focus of their research was in the mid-latitudes. Now, one thing that I like to talk to people about was what happens with this is that the mid-latitudes are dynamically quite different from the tropics. And so when all the research started, which was focused in the mid-latitudes, then their focus was going to be on stuff that happens at these latitudes and not things that happen in the other latitudes. And one of the reasons why this happens is because when you look at a map and you sort out the map socio-economically, for example, sort out first world and second world, third world countries, as you see often in Google, this is a figure that I got it from Google, you'll see that first world countries are pretty much, for the vast majority of them, in the northern hemisphere, mid-latitudes, and then a lot of the developing nations, the majority of developing nations are actually in the tropics. So with this taken in mind, do know that this has had profound consequences on how we have carried our research with a lot of the economics and a lot of the resources to carry out research in atmospheric science being mostly in these first world countries in the mid latitudes, where the tropics were kind of like left off as like a second thought. Let's just leave it as an afterthought initially, with it not being the focus of our attention until much later on in the 20th century. And I just wanted to like throw in a little bit of a shout out to a new manuscript that's being prepared by Twett et al., Judy Twett and Dargan Frierson and myself. We have been trying to put this together for a couple months. But another major inhibitor to tropical research has been that a lot of the funding agencies that funded mid-latitude research also funded eugenics research. So these are people that actually wanted to just fund people in Europe and the United States. So if you're interested in the social, economic, and racial aspects of like the history of atmospheric sciences, this manuscript that is being prepared by Twett et al. Should be an interest. And if you're interested in it, you can send me a message, and whenever this manuscript gets accepted or gets submitted, we'll send you a copy. So what about the tropics? So I mentioned earlier that the research in the mid-latitudes started mostly taken seriously like in the early 20th century. So research in the tropics wasn't really taking off. It didn't really take off until World War II. And the reason that has to do is because of Japan and all the stuff that happened with the warfare in the Second World War. Then the US that started to get interested in actually understanding the tropics and stuff that happened in the tropics. So this is a picture from the 1940s. And like I mentioned earlier, the research didn't take off until World War II. And the first really well-documented school of tropical meteorology actually occurred in Puerto Rico, which actually after doing some research, kind of surprised me because I grew up in Puerto Rico and I never heard about that. So this is kind of like something that has been getting lost to society to some degree. But this was a really important school of tropical meteorology. It had participation of all the big names back at the time, including Rossby and others like Herbert Real and others. In fact, the first book in tropical meteorology was written by Herbert Real, which was a participant of this tropical meteorology school. And Herbert's preface, this tropical meteorology book, which I actually have a copy, you can find a copy online, had some really golden quotes here about what people thought the tropics were back in the day. So here's a picture from the preface of the book, and I'm gonna like put a little highlight, a little box on an area that I want you guys to read. So this first book on tropical meteorology was written in 1954, and it does detail what we knew from the tropics back then. And it talks about World War II, Puerto Rico, modern tropical meteorology. And what I wanted you to read is this little box here, which says, in the past, weather and circulation in the low latitudes had been regarded as a steady concept except for the occasional hurricanes. And then, you know, the urgent demand from the army was really what led to the change, because we really wanted to understand things. And as they were flying and doing things in the tropics, they realized that this is not the case at all. But it does come to tell you that back then, as you know, it's not that far in the past as World War II. We're talking about 1940s. People thought that the tropics were kind of like sunny, you know, sunshine and hurricanes every now and then, and with no really interesting dynamics actually going on whatsoever. So, and the second box says that the military forces eventually just found that the weather on a serious scale just didn't happen in the tropics, and but then afterwards, as the observations came out, they realized that this was not the case, that things are actually did happen on a large scale that we're interested. And then they started asking the question, so how did this happen? And how can we predict this in a way that can actually help society? So if you look at a satellite image like the one that I'm showing you now in the image, you know, like we kind of take for granted these satellite images from like the geostationary satellites, and you look at all this that's going on. You obviously see that the mid-latitudes are a very dynamic area, and that you see like things like storms happening here in the northern mid-latitudes, even in the southern mid-latitudes. You see a lot of activity, but you take for granted that you see a lot of tropical activity. You just see all these thunderstorms. You see the intertropical convergence. You see the Indo-Pacific warm pool, and to a lot of people, you just see that, you know, and you either don't blink an eye, you know, you just see it, and of course it has to be this way. And to other people, that you see all the dynamics that are going on, and you see a very dynamically rich region that is like very different from what was described as far back as the World War II era. So clearly, the reality of the tropics is very different from these initial concepts that people had. All right, it's really hard to imagine a tropical atmosphere that is as steady as boring as it was initially depicted, by people that came into this school of tropical meteorology back in World War II. And this brings us to today's talk, because what I mentioned is that there was this preconception from the 1940s, and we have our 2020, 2021 understanding. So we're talking about what 80 years into the future. What has changed? We're going to talk about like how things have changed and now how things have become much more rich than what it was back then. So the purpose of this talk is to just show you how rich and dynamic the tropics are. But in order to really get an understanding of how rich and different they are, it's important to actually start by reviewing the mid-latitudes, because chronologically, we have been studying the mid-latitudes for far longer than what we have been studying the tropical area. All right, so let's place everything into context. So let's just give a few slides about the mid-latitudes. So let's speak about this in a little bit. So if you've taken a class in atmospheric dynamics or even an introduction to atmospheric sciences, one of the first things that you get in terms of like atmospheric dynamics is this concept called geostrophic balance. And when we talk about geostrophic balance, what we discuss is that there's like a balance between two forces. You have the pressure gradient force, which when you have a low pressure, the air wants to go towards a low pressure. And then you have the Coriolis force, which is a deflective force, which essentially wants to like deflect the wind and towards the in the northern hemisphere towards the right of where it is heading, for example. And so here's a diagram to the right. You see like a high pressure in the middle and a low pressure on the flanks. And in reality, you have this bump of water. Let's just assume that it is water, and all the water just wants to slush away from the center of high pressure. But when you have geostrophic balance, when you have a really strong Coriolis force, the Coriolis effect actually starts deflecting the water as it kind of flushes out from the high pressure. And eventually it reaches geostrophic balance in such a way that you still have that pressure gradient force. You still have the force trying to push the water into the low pressure and away from the high pressure, but then you get the Coriolis effect that's deflecting the air sufficiently that it's just rotating around this high pressure. And this is like a bit of a first order balance. You do have additional forces here. It's not quite exactly correct, but you have the right idea. So in the mid latitudes, this is the dominant balance. You have the Coriolis force and the pressure gradient force balancing each other out. But here's the thing, and I just mentioned that this is like a good idea, but not exactly 100% right. And that's because you actually do have a certain amount of acceleration just because you have curvature. Remember that when you have a curved flow, the flow will have a little bit of an acceleration just to maintain that curvature. So the curvature actually has like a centripetal or a centrifugal acceleration depending on which perspective you're looking at. It's the same thing. Let's just mention it's the centrifugal force, for example. And that centrifugal force will give you some amount of acceleration. And that acceleration is actually quite important in the mid-latitudes because this small deviation from geostrophic balance actually is what drives all the day-to-day variability associated with what we refer to as Rossby waves. So here's an image from Climate Reanalyzer just showing the winds in colors with the little vectors. And you see all these meanders that are going up and down in latitude. These are referred to as Rossby waves that you see in day-to-day variability. And these Rossby waves are driven by small departures from geostrophic balance. That's what's really accelerating the flow in these regions. So now our momentum equation has changed. We still know that this right-hand side terms that define geostrophic balance are the largest terms in terms of magnitude, but that there might be small differences, small residual between these two terms. And when you add them up, you'll get the small residual that is actually describing the acceleration of the particles that are moving in this jet stream here. All right. And I mentioned one thing that's quite important, and that is that this acceleration is small. So you still have geostrophic balance to leading order, but you have a second order residual, which is much smaller, but still very important. So when you study mid-latitudes dynamics, you find that when you do scale analysis of, say, the momentum equation, like you see here on the screen, you find that, for example, these two forces are like leading order balance. So they're like order of magnitude 1 when you non-dimensionalize and do whatever. And then you find that the acceleration is of order Rossby. And then this Rossby number is defined here on the bottom is just the ratio between the zonal wind and the Coriolis force, the planetary vorticity F, and then the horizontal scale of your disturbance. And in the mid-latitudes, the Rossby number is often a lot less than 1. It's about 0.1 or less. So you find that the acceleration is way smaller than the two leading forces. And that's what leads to quasi-geostrophy. And this is what we refer to as quasi-geostrophic motions. They're two leading order geostrophic, but you still have this small residual, which is not negligible and very important to drive the accelerations that you see on a day-to-day basis. All right, so the take-home point here is this Rossby number. This Rossby number is really important to the mid-latitudes. So, and it tells you how geostrophic the motions are. If you have a really small Rossby number, then you have quasi-geostrophy. So what happens in the tropics? How are the tropics different from the mid-latitudes? So in the tropics, you have an important but nonetheless different set of balances that are very different from the mid-latitudes. And I like to think about them as two sides of the same coin. In geostrophic balance and quasi-geostrophic motions in the mid-latitudes, you get that the geostrophic balance is the leading order balance, and that you get that this is a balance between the Coriolis force and the pressure gradient force. In the tropics, we get the other side of the coin that happens because the Coriolis force is really weak. And we refer to this as the weak temperature gradient balance or the weak temperature gradient approximation. And I'll discuss this in a little more now. So here's a map of the tropics. This is the 500 hectopascal temperature distribution. And the thing that's really key about this plot is just how homogeneous the temperature distribution in the tropics is. You essentially see the same color. And this is a 500 millibars hectopascals is the mid-troposphere. When you look at the mid-latitudes, you see that the color is quickly changing. So that tells you that there's like a very strong temperature gradient, as you would expect from the thermal wind relation in the mid-latitudes. So you are seeing strong temperature gradients in the mid-latitudes, but in contrast, temperature gradients in the tropics are very, very small. All right, so it's pretty smooth. I will say that maybe between 15 north and 15 south is pretty homogeneous. So we're just going to refer to the weak temperature gradient regime to as this equatorial belt between 15 north and 15 south. All right, so what's going on in this region? Why do you have a balance? Why do we have weak temperature gradient balance? So unlike the geostrophic balance, which is a balance in the momentum equation, weak temperature gradient balance is actually a thermodynamic balance. So it's actually a balance that occurs in the thermodynamic energy equation. And in this balance, you have a balance between adiabatic cooling, which is this left-hand side term. This is just the vertical velocity and pressure coordinates, omega. S sub P is the static stability. And this adiabatic cooling approximately balances the diabatic heating. So as you have a cloud, like you see on the diagram here on the right, you have latent heat release from condensation and other processes that are occurring within the cloud. And that is diabatic heating. And then within the cloud, you have strong vertical motions. So that's that omega over there, and that the upward motion and the adiabatic expansion that parcels are experiencing as they go up in the updraft are actually offsetting the amount of latent heat release that you're getting from condensation. And this happens because gravity waves develop within the convection and spread away all that energy that's being released away from the convection into the surrounding environment. Now, if you're not familiar with this, I'll show you in the next slide how this happens. So this is a diagram from a paper in review, Adames and Maloney, current climate change reports. And here on the right, we have a heat source, which is shown as the pink line here. And then in the blue, this is like a temperature anomaly that's been developing because of a region of heating. So you can imagine the pink line as like a cloud. And then you can think about the blue as like the temperature anomalies that's being developed because of the warming in the cloud. And then the vertical velocity is this red line that's underneath. So here you have that you turn on this heat source, this cloud kind of appears at time equals 0. And then this first panel is time equals 5. And then you have 30 minutes. And then you have an hour and a half in the bottom. And you see that the following evolution happens. You start seeing that at 5 minutes, you have like a region of vertical ascent. So you have ascent in this center region here, and you have a flanking region of subsidence that's just surrounding this region of heating. And then you start seeing that there's a bit of a warming in the region. Okay, so far it makes intuitive sense, right? You have a region of heating within the cloud, and then the cloud actually starts warming up, and you start seeing vertical circulation associated with this heating. 30 minutes afterwards, what you see is that now you've warmed up this region that is about 200 kilometers across. So you see that all of this has warmed up. And now you've seen that within the cloud, you have a vertical velocity that has essentially balanced the heating. So I actually made the scale for a reason. So when the whole thing becomes balanced, the pink line and the red line overlap with each other. So now you're seeing that the whole cloud is now balanced. So you're not actually getting any heating in the cloud anymore. Instead, you see the subsidence that has moved away from the cloud. You can call this like a subsidence front or something like that. And then the subsidence front seems to be the leading edge of this warming. All right. So you're seeing this warming associated with this subsidence. This is what we call a gravity wave response, actually. So you essentially have a cloud, and the cloud is actually like punching through the sky. And as it punches through the sky, it actually generates these gravity waves that are actually causing subsidence. And as they cause subsidence, they're warming the layer because you're actually adiabatically compressing it. But that actually is not confined to the cloud. It just keeps propagating away from it, warming the whole layer. And after an hour and a half, it's actually propagated away from the whole region. And now the whole region is in balance. You can see that the vertical velocity now perfectly balances the heating. And now you just adjusted the temperature slightly higher than what it was before, maybe like a quarter of a degree, a little bit, or maybe a little bit less, but it's definitely warmed up the column a little bit. And what we refer to weak temperature gradient balance is what happens in this end state over here. After some time scale tau g or tau WTG, which is defined as L over C, C would be the phase speed of these gravity waves. So this is like about 50 meters per second. And then L will be the length of this domain. So in the case of this domain, tau g turns out to be about an hour and a half. And then L will be 300 kilometers. And then C will be like 50, which is the gravity wave phase speed. So after this time scale, the whole domain has adjusted to what we refer to as weak temperature gradient balance. So WTG is just essentially a balance that happens in the thermodynamics because gravity waves exist and they actually just redistribute energy around, homogenizing the temperature profile always. And this happens because the Coriolis force is very weak. Otherwise, you would actually have a Coriolis force deflecting the gravity waves, causing geostrophic balance to occur otherwise. So unlike the previous diagram that I showed you, in which you actually get a bulge and the bulge actually is in geostrophic balance, what happens in the tropics is what you see in the diagram here on the right. You actually get these gravity waves and they actually start emanating away. So you can think about this like a subsidence front, like here in the image. So you can imagine that subsidence kind of like really propagating away. And then as it propagates away, this whole layer is being warmed up. All right. So this leads to a balance in the thermodynamic equation. So what we're talking about here is that you have like a little bit of warming. So we know that the temperature evolution matters, but the leading order balance is these right-hand side terms that you see here in the thermodynamic energy equation. And if you do scale analysis in the same way that you did in the mid-latitudes, you will find the following balance. You will find that to leading order, you have the weak temperature gradient approximation. These are way bigger. They're order 1 if you make them non-dimensional. And then the temperature evolution, this dt that you see here, is the part of the second order balance. And it's defined as the ratio between the square of this gravity wave adjustment timescale. So the timescale in which gravity waves adjust the system to the WTG approximation divided over the timescale of your wave or your phenomena of choice. So if this tau g squared over tau squared is much less than 1, in the same way that the Rossby number is much less than 1 in the QG approximation, then you have that WTG balance occurs. So like I mentioned, you will have WTG approximation occurring if your gravity wave timescale is much faster, much shorter than the timescale of any disturbance that you're interested in. And this is actually like the flip side of the Rossby number. So the Rossby number occurs for very large scale phenomena that are actually moving fairly slowly in time. This actually is kind of similar, but different in some ways in that it is actually more related to the gravity waves. So if the gravity waves are way faster than the scale of the disturbance that you're analyzing, then WTG actually applies. So, but here's the trick. Here's where things get hairy. I just mentioned that there was a cloud and the cloud created gravity waves and the gravity waves emanated away and created WTG balance. So this, I kind of like am hiding a little bit of important details here from you because I wanted things to start out pretty simple, right? We're just assuming a cloud and then the cloud just exists, you know, and it's just there heating up the atmosphere. It's not really doing anything dynamically in itself. But the reality is very different from that. In reality, clouds appear, they evolve, they become deeper, and then they stop, you know, they rain out, they evaporate, etc. So things are way more complicated than that. But nonetheless, this weak temperature gradient approximation has given us some really profound insights to how tropical convection actually happens in itself. So I'm going to move on now and talk about how tropical convection might evolve and how the weak temperature gradient approximation applies to it. So new work by Faiz Ahmed and David Nealon at UCLA has shown that you can actually explain some basic properties of convection by using the buoyancy of an entraining plume. And the entraining plume actually is quite useful because it actually combines two properties that seem to explain a lot of the convection sensitivity in the tropics. So there are two things that really drive convection in the tropics. And these are small fluctuations in temperature that occur in the troposphere. And then the other one is the environmental humidity. And if you take an entraining plume, then everything actually gets combined neatly into a single framework, and you get this equation that you see here on the left. So you get that the buoyancy of an entraining plume is just the equivalent potential temperature of an updraft, and the theta E actually contains both information about water vapor and temperature. And then you get the difference between that theta E of the updraft and then the saturation theta E of the environment. Now, the saturation theta E of the environment is just a function of temperature because it's just the saturation component. So you got the moisture and temperature of the updraft minus the temperature of the environment. This kappa that you see here is just a constant. And then again, you get it divided by the theta E of the updraft. And this equation, we were able to derive it in a new paper by Adames et al. In 2021. And one of the neat things about this buoyancy metric is that if you average it over the lower troposphere, you see that it actually explains not everything, but a good chunk of the variability in rainfall in the tropics. So you see that if your buoyancy is very negative, you actually get very little to no rainfall. And then once you start getting to zero or getting into positive numbers, then you ramp up very quickly, pretty much exponential way. Becomes kind of quasi-linear after a while, but it's pretty exponential actually. So why is this plume buoyancy actually kind of nice? And the reason is because it contains two important bits of information about how tropical convection develops. One of them is that you need your temperature lapse rate to actually favor convection. So you need like your the CAPE, your available potential energy, to be more than zero, but you also need your convective inhibition to be sufficiently low so that clouds can convect. But you also need a pretty humid troposphere because your cloud is actually interacting with the environment. It's actually entraining. And if your environment is super dry, that entrainment is going to kill off the buoyancy of the cloud and actually make it not develop. So this plume buoyancy framework actually captures these two properties. So one of the things that Ahmed and et al. Did in this 2020 paper was that they found that these two things, when they put together, can explain some of the properties of convection. And one of the things that they found is that the convection is sensitive to convection, but it's an adjustment that happens actually very quickly. So if you look at the profile that you looked at in the last diagram, you find that this is like a pretty steep curve. And if you take the relationship between it, you will find that there's a slope here. So this is a pretty steep slope. And this slope actually is indicative that precipitation is incredibly sensitive to buoyancy. Incredibly sensitive. It's just an incredible sensitivity. A small change in buoyancy can actually either quickly cause convection or quickly shut it down. So what that means is that actually the troposphere responds very quickly to convection. And in fact, if you take a time scale and find the time scale analytically, you will find that the adjustment time scale, the time scale in which the atmosphere eliminates buoyancy from the column, is very fast, in the order of a few hours. And this is consistent with a concept that has been referred to in the literature as convective quasi-equilibrium. This is something that has been brought up in the literature since the 90s at least, or even before then, maybe in the 70s. And what this tells you is that if you have a convective cell, say that you have these clouds here, they're kind of mixing with the environment, you have like a relative humidity profile and a temperature profile, you can have one of these two things. You can either decrease the temperature of the lower troposphere, that kind of like increases the CAPE or reduces the convective inhibition. And then all of a sudden your clouds become very buoyant. But then because the clouds are becoming very, very buoyant, you will actually start getting this gravity wave response that actually warms up the column just a little bit. But that happens so quickly that actually that cooling that you see here gets eliminated very quickly by this gravity wave response, for example, and then you warm up the column, and that actually shuts down the convection because you no longer have that cooling that drove the convection to begin with. But here's the thing. When you get to this final state, you actually have done two things. You not only have changed the temperature, you've also changed the humidity profile because you created that subsidence front that we discussed earlier, which also dries the column. So that final state is actually not the same as the first state. You can actually have a state that's actually a little bit warmer, but also a little bit drier, and now your buoyancy has been reduced again. So the first state and the last state don't necessarily have to correspond to each other. You can actually have very different profiles depending on how the gravity waves respond and other things that are happening in the column in the first place. A similar thing happens on the right-hand side when you change the relative humidity. Again, you're getting this convection, and it's adjusting to the convection is changing because the humidity is now higher, and so you're entraining less, so they can actually grow deeper. But then after all that happens, you get the gravity waves and you have everything, and then the whole thing restabilizes again. And this happens on the order of just a couple hours, like 2 hours or so. So this is very fast compared to the time scale of a lot of things that we actually see happening in the tropics. So the work that I just got published, and I'm going to put it on the end. So this Adames 2021 paper, what we did was that we wanted to know how this destabilization process can happen with the process of tropical motion systems happening. So you have these gravity waves, Rossby waves, the MJO, when all these things are moving across, how does this buoyancy profile evolve in the first place? And we got this equation over here that I'm going to describe now. So this BLDT is just your evolution of buoyancy, of the plume buoyancy. So this is the entraining plume model I discussed again. This N is a constant. And then you have these three time derivatives here, where HB is the moist enthalpy or moist static energy of the boundary layer. So this is like the near surface layer. And then these two quantities that are here that have the subscript L are the lower free troposphere components. So you got this QL, which is the specific humidity of the lower troposphere, and then TL is the temperature of the lower troposphere. Now, this capital L is just the latent heat of vaporization. The CP is just the specific heat of dry air. And then you get these three other constants. You got this pi tilde, and this gamma Q, and then this gamma T. These are the interesting parameters. So it turns out that this pi here is about close to 1. It has a value very close to 1. And this gamma Q has a value of about 0.75. So it's kind of close to 1, but not exactly 1. But this one, this gamma T, is the interesting one. This has a value of 4. And what these three parameters are giving you as information is the sensitivity of buoyancy to changes in the three parameters. So it's the sensitivity. So pi is the sensitivity of buoyancy to changes in the moist static energy of the boundary layer. And then this gamma Q is the sensitivity of buoyancy to moisture in the free troposphere. And then this TL is the sensitivity. This gamma T is the sensitivity of buoyancy to changes in temperature in the free troposphere. And this last one has a value of about 4.2, 4.3 or something like that. So it turns out that the troposphere buoyancy is actually incredibly sensitive to small changes in temperature in the free troposphere. So what does this mean? So let's put everything together. Moist static energy actually contains temperature and moisture information. So really there's two things that are driving the convection in general. It's just the temperature and the moisture fluctuations. And it turns out that buoyancy increases if you increase the moisture content of the free troposphere. So ultimately buoyancy is, very sensitive to water vapor, which is actually a result that we were expecting. But it's also very sensitive to fluctuations in temperature. And it's actually incredibly sensitive because it actually has a factor of 4. So it's actually most sensitive to temperature than anything else. But it turns out that because the atmosphere is in weak temperature gradient balance, these temperature fluctuations are very small. So when you compare these three things, in the end, they're actually all comparable to each other. They have actually contributed about the same. So it turns out that the evolution of buoyancy and hence the evolution of precipitation is actually a result of two things that are happening in the troposphere. One of them is because water vapor is evolving in time, and so the entrainment is changing. And then the other thing is because of departures from WTG balance. And this actually has a lot of parallels to what I mentioned earlier about quasi-geostrophic motions. Geostrophic balance is what happens at the leading order, and that actually explains the state of the wind field and the geopotential at any given time, but its evolution in time is actually given by this departure from geostrophic balance, the quasi-geostrophic motion, because the acceleration is part of that second order balance. And the same thing happens here, that it seems that the convection evolution is actually partly explained by these departures from WTG balance. So here's a few ways in which the troposphere may be destabilized by convection. On the left, you can actually have horizontal moisture convection. So you have this blue area that's really humid. You can have a wind field that's just blowing that moisture to the left, and that moistens the free troposphere, and that can lead to increase in buoyancy and hence convection. The other thing that can happen is that you can have like winds and increased fluxes of moisture. So you can have evaporation increasing or the surface sensible heat flux increasing, and that increases the moistatic energy of the boundary layer, and that also increases the buoyancy. And last but not least, you can actually have gravity waves, which are part of this adjustment towards the WTG approximation. And then these gravity waves could have either a subsidence front that actually warm the troposphere and suppress convection, or you can have upward motion within these gravity waves that actually cool the troposphere and then destabilize it and lead to more convection. So here are 3 examples. One of them is actually just purely WTG, just moisture related. And then one of them, the one on the right, is from departures from WTG. So I wanted to give a few last slides as to how this all comes together into explaining how tropical motion systems evolve through time. So I just mentioned that there's 2 pathways in which you can actually evolve the buoyancy, and that can lead to the evolution of tropical motion systems. That actually means that there's many pathways in which motion systems can modulate convection, and ultimately this means that there's probably a diversity of tropical motion systems. So what leads to this diversity? So that's what the last thing that we wanted to tackle in this talk. So it turns out that there's actually 2 regimes in the tropics. This comes from work that Dave Raymond and others have done. And they've actually found that there's likely 2 regimes in the tropics. One is a balanced regime. The evolution in the balanced regime is slow, so they propagate slowly. They tend to be balanced, so they tend to be Rossby-like. They have to have balanced wind fields that are not evolving very quickly in time. And they found that in this balanced regime, moisture is really important for the thermodynamics. So you have a picture here of a satellite image. So the white stuff is clouds, and then the red stuff is actually regions of enhanced water vapor. And you see here that all the convection is kind of tightly clustered to this region of enhanced water vapor. This actually corresponds to an MJO event that was captured at some point in time. I forgot when. And then you have this second regime. So they have this balanced regime, moisture is important, super balanced, slowly evolving. And then you have this unbalanced regime where things are actually evolving very quickly. You have short time scales, propagation is fast, the wind field is unbalanced, which means the acceleration is really important. So you're getting accelerating fields. And then this region seems to be largely driven by departures from WTG, so which means that small temperature fluctuations are key to the thermodynamics of these motion systems. So you're getting one regime that seems to be in WTG balance, and moisture is really important, and then another regime that is actually not in WTG, and then these departures from WTG are very important to the precipitation in these systems. So how do these systems exist? What happens that they actually exist? Why are they both occurring in the same location in the tropics? So, and this is a diagram from Adames and Maloney in review. And this is a synthesis of the research that a lot of scientists have done in the past. This is what we found. So imagine that you have some kind of mesoscale convective system in the tropics, and you have, an updraft, and you have your cloud here in the top, and it's raining. You got your stratiform rain area, you got your convective rain area. Because this region is convecting, you turn on the convection and you get these gravity wave responses that I mentioned earlier in the slide. So it turns out that the deeper gravity waves move faster than the shallower ones. So you get this gravity wave response in orange here. So this is like a very deep gravity wave that moves very quickly. And then you get these shallower gravity waves that are associated with the more stratiform rainfall. So you're getting some rain evaporation here that's cooling. So you're getting kind of like the opposite of the subsidence front that we saw earlier. You get like an upwelling front, and then you get this heating from the stratiform region. So you get several different types of gravity wave responses depending on the type of heating that you're getting, reheating or cooling that you're getting from this rainfall region here. And then in the bottom, you see the humidity profile, and I'm just in green, and then you get the convective inhibition here in orange. So what happens in these 2 regimes? So let's imagine first our convectively coupled gravity wave regime. What happens if this regime is evolving so quickly that we can't have WTG happen in it? So this first regime, we're just going to call it the convectively coupled gravity wave regime. In this regime, our tau G or our tau WTG, which is the timescale in which weak temperature gradient balance occurs, is much longer than the timescale in which convection actually gets eliminated from the column. So this tau QE, we're going to refer to as the quasi-equilibrium timescale. This quasi-equilibrium timescale is so short that actually you can't get WTG. So what happens here is that your profile cannot adjust to WTG, and so you get these cooling regions that may actually excite new convection. So you have the convection die off because it's dying off super quickly, more quickly than WTG can happen, but then these expanding gravity waves can then excite new convection downstream. So you're just getting this gravity wave that's just expanding outward in a very fast and systematic way. And as it expands outward, it's just really exciting new convection as it goes downstream. This is going to be our convectively coupled gravity wave regime. In contrast, we have the moisture mode regime, which is when your convection lasts so long that WTG can happen. So all these temperature anomalies can get eliminated, and then temperature doesn't play a role in the convection of these systems. In this case, your temperature gets smoothed out. So you see that the orange line becomes very smooth. And then the only thing that can explain the distribution of precipitation in these regions is the distribution of water vapor. So in this case, your precipitation is actually being focalized because this is the area where the humidity is the highest. In this case, in the case of the moisture mode, the system evolves very slowly. And in the gravity wave regime, it evolves very quickly. So one thing I didn't mention before is that this convective duration, tau QE, actually has a dependence on something. It's not a fixed constant in space. And it's actually inversely proportional to what we refer to as the gross moist stability. And the gross moist stability, you can think about as a demand minus supply argument. So the higher the gross moist stability is, the more demand the atmosphere has for rainfall to occur, but the supply is too small. So in an atmosphere that's really humid, you actually have a very large supply of water vapor, and to maintain the demand that the convection needs to stay. So the demand is the amount of water vapor that convection needs to stay, and then the supply is the amount of water vapor that's being converged to maintain the precipitation. So it turns out that if you have a really humid atmosphere, this M tilde is really small. So convection can actually last a lot longer. So it turns out that in really humid atmospheres, this parameter is very small, and tau QE becomes larger, and so the moisture modes become more possible to exist. But if this time scale is too short and the atmosphere is a little bit too dry, then you actually get gravity waves instead. So just to show you a little bit of an animation of how something that is moisture mode-like, or at least the literature thinks it's a moisture mode. Here's an animation of an MJO event. And you can see that this a very balanced wind field. It looks like Rossby waves. You get these cyclones. This is, by the way, the water vapor. And you can see this evolving through time in a very slow way. You can see here in the time and the title that this is an animation that's taking several weeks at a time. So we're thinking about something that's evolving very, very, very slowly with time compared to the other regime that's actually just blasting off at a very fast speed. So if you compare this to the WTG regime, then you can, the non-WTG regime, the gravity wave regime, this is the evolution, for example, of a Kelvin wave. The dark line is the outgoing long wave radiation. You can think about this as the convection, and this is like 2 days. So you can see that within 2 days, the convection has moved several thousand kilometers across the West Pacific Basin. And that's compared to the previous diagram in which the whole thing maintained itself over the Indian Ocean throughout about a 2-week period. So we're comparing something that is very quickly evolving versus something that's very slowly evolving. And these two things are happening in the tropics together. There's more. There's a little bit of thing that I wanted to add at the end here. When you have Rossby wave-like disturbances, this gross moist stability, this demand minus supply argument does come into play into the dynamics of these Rossby waves. And you get something that I refer to as the gross potential vorticity, or the moist potential vorticity. And it turns out that as the gross moist stability becomes smaller, potential vorticity becomes less important to the dynamics of these waves, and the evolution of moist static energy, or moist enthalpy, so the thermodynamics, become more important. And what we found in a recent study was that this gross potential vorticity is just the sum of the regular potential vorticity PV times the GMS, this gross moist stability, plus 1 minus GMS, the MSC. So as this M becomes smaller and goes towards 0, the MSC becomes more and more important. In the mid-latitudes, where M is actually quite large because the atmosphere is a lot drier, then PV is way more important than MSC to driving the evolution of waves and all these other phenomena that you see. And this has important consequences because PV and moist static energy lead to different mechanisms for growth. And this is where I'm going to end here with this latest paper that I've been working on a 2-layer model. And what we found is that if your atmosphere is really dry and you have a region of easterly shear, so you have winds that are becoming more easterly with then if your atmosphere is dry, you get a wave that actually tilts with height and has a vertical profile similar to what you see here in the A. However, if your atmosphere is really humid and moisture is prognostic in your equations, this actually doesn't happen. It doesn't really happen at all. Instead, what you see is an evolution that's more consistent with the diagram on the right. You get this vertical stacked cyclone that looks like a tropical depression in which the convection actually is moved towards the center of the cyclone. You get a lot of humidity near the center of the cyclone, and the whole thing is vertically stacked, unlike the vertically tilted structure that you see in baroclinic instability. So the one thing that I wanted to end with you guys is that just by including water vapor in a simple model of the atmosphere, you can say that when you change the shear and you make your environment really humid, the dynamics change completely. And that, I think, is like a pretty outstanding result about how things actually operate in the tropics in regions that are really humid. It really are these thermodynamics that are associated with the convection that are really essentially moving the truck altogether. Whereas like in the mid latitudes, you actually have these interactions in the upper and lower troposphere associated with vorticity and position vorticity. These are the main drivers. But in the tropics, we cannot disregard the evolution of water vapor. And to just to give you a little bit of a context, this is a paper from Cohen and Booz. And the whole importance about this is that in the Asian monsoon, where you see this easterly shear, you actually don't see tilted cyclones. You actually see vertically stacked cyclones like the ones that you see on the right. So the potential vorticity is shown in colors, and the temperatures in contours, and you see that this is a vertically stacked cyclone. So by the way, the longitude is in the X and the height is in the Y. So what this suggests is that maybe the thermodynamics completely change the behavior of systems in the tropics in regions that you have shear. And that leads to this last diagram that actually synthesizes everything. What we believe, or at least I believe, and a couple of my colleagues believe, is that you may be able to explain the diversity of tropical motion system by a few parameters similar to the Rossby number. So you get gravity waves where you have a lot of acceleration, Rossby waves in regions that are balanced. That's actually explained by the Rossby number that you see on the right. And then you get the gross moist stability on the bottom that I mentioned. And that actually explains the difference between regular Rossby waves and moisture modes with some mixed behavior happening in between. And then the stuff that I mentioned earlier about the adjustment towards WTG, explaining the differences between gravity waves and moisture modes. So when you combine all of these parameters together, you get like a triangle or a pyramid, and that pyramid may explain some of the diversity that you see in the tropics. And again, what I mentioned earlier, that this tau QE is actually a function of the gross moist stability. So these two things are not independent from each other. So what this means in the end is that maybe there's just a few parameters. Maybe all you need to know is the humidity and the mean state and all these other things, and maybe that can explain a lot of the diversity that you see in the tropics. However, I will say to the caveat that this is super idealized, and this is a paper in review, so who knows what the reviewers are going to say. And with that, I will lead you with what we think might happen in the future. There's a lot of great research happening here. A lot of you guys are looking at machine learning. A lot of you guys are looking at convection details themselves. I think that in the future, we're just going to combine all these things together, and maybe we're going to get some novel insights and see how all of this comes together and really brings out a very lucid picture of what the tropics behave like and what are the hidden hands and all the mechanisms that are driving all these motions that we see at the low latitudes. So with that, I leave you with the conclusions. I think I'm running low on time, but I'll take any questions if there's any from the audience. Thank you so much for your time.
Thanks, Angel. So feel free to either raise your hand on the Zoom list or type your question directly into the chat, and we'll call on you in succession. Questions for Angel?
Yeah, this is Jimmy. Could I ask a question?
Sure.
Yeah. First, it's an excellent talk. Give a very, very nice new view on how to think about the wave motion or tropical variability from combining this Rossby number and this moist number you define. And I would like to know more about this concept by going back to these two examples you show. And near the end, one is this inside the Indian Ocean, the other is inside the Western Pacific. Right, those two areas, yeah, this one and this one. This one is MJO, right? And
yes.
then the next example is the other kind of mold in the Western Pacific, and
Yeah, it's a
that
Kelvin wave.
one, right? So, but I thought that in your previous slide, you say that the key reason to separate, to give rise to different mode depends on the abundance of moisture, right? Depends on how moist the atmosphere is. So I thought the Indian Ocean and Western Pacific are both probably equally moist. Is that the accurate way to say it? And if that's the case, why these two regions give rise to a different mode in your example?
So this is a great question, and the answer to that is, well, the short answer to that this is still a topic of ongoing research. The long answer is that we suspect that the mean structure of the convection in these two systems is different. So the MJO tends to have a more vertically stacked, deep with stratiform, kind of like single mode vertical structure, whereas the Kelvin wave has to be very tilted and evolves from like shallower to deep to stratiform. And it's mostly like this second baroclinic mode where you have this cooling in the lower troposphere and heating in the upper troposphere that drives the Kelvin wave, whereas the MJO, that's not necessarily the case. So a lot of the driving motions that causes the time scale to change actually is related to convection. That's something that I didn't bring up because I actually forgot about pretty much. But it is very important. So like the ability for the atmosphere to adjust to a weak temperature gradient balance has to do a lot with how the profile, vertical profile of heating. If your heating is very homogeneous and the troposphere has the same sign, adjustment to WTG occurs much more quickly than when it's not. So if you have more complex structures in the convection that evolves from like shallow to deep and then stratiform, that actually takes longer to adjust to WTG. So a lot of the waves that you see, they all couple to convection, but the way in which the convection looks like and the way that it looks like in a cross-sectional evolution, actually the details are slightly different. But these slight differences in the details are very important.
So in the Indian Ocean, the convection, vertical structural convection is more complex than the vertical structural convection over the Western Pacific. Is that what you are saying?
Not in the ocean basins, but associated with waves. So like the convection, the morphology of the convection in the MJO actually is different from that of a Kelvin wave. So the way that so you might have a convection, flare up all together in one region, and then you'll get an MJO that will kind of keep certain convection types with itself, and then the Kelvin wave will keep the other ones. So they all can start together, and then they evolve differently.
I see. I got it. Thank you. Yeah, it's excellent.
Okay, thank you. Oh yeah, that's I forgot about this last slide. Any other questions?
I'll ask one if there's silence. So like, maybe this is not easy, maybe you can't answer this, but how, I'm very much aware that there's been this like mini revolution in tropical dynamics over the last decade that, we can foresee much needed textbook chapters that feel like Holton, and you showed a beautiful example here with like a basically moisture modified 2-layer model where we can start to say profound things from traditional scale analysis about how disturbances in easterly shear will behave depending on how their balanced flow interacts with the moisture field. So is there a similar disruption happening in parallel towards our understanding of how convective extremes will change with climate that's happening in lockstep, or is that not here yet, or do you anticipate it, or what's your outlook for the
I think it is
with climate change?
I think it's already happening, and I've seen some brief. I can't tell you because as a topic I'm less familiar with, but I think I've seen some already kind of like hints of like how the WTG approximation is being used to understand how precipitation will change in the future climate. I think I saw a recent paper on this, but I'm not 100% sure. But I think it is happening. Some people are already looking into this.
Do you have any sense of consensus emerging that's like, give us... faith in should alter our faith in current GCM predictions of how extremes will change in the future based on this new way of viewing the dynamics?
I don't think so. I don't think there's any consensus. I don't suspect. I suspect that there's no consensus emerging yet. Like it's like the MJO. I think like the core idea is getting there, but there's still like a lot of different thoughts about the details about how things are driven. Like it's kind of like it's kind of like we have the layout of the vehicle laid out, but like we don't know what kind of motor we want to have. What kind of radiator we have, what kind of sound system it has. But the layout of the car is there.
Thanks, Anha. We have time for one last question if anyone has one.
Maybe I can ask a quick one. So near the end of your talk, you showed that the triangle diagram, right? That which use two parameters to determine the regime of your wave activity. I was wondering, does this one only apply to tropical region, or it can also apply to mid-latitude?
I think it can apply to mid-latitude. The scaling on the diagonal is different. I actually did this recently because preparation for class and other things. So the scaling of the thermodynamics changes as geostrophic balance becomes of leading order importance in the scaling of the equation. So this ratio that you see of the tau WTG over tau QE, that actually changes a little bit with the mid-latitudes, but the same idea still applies. So I would suspect that you can still think of something similar in the mid-latitudes. I will say though that because the mean concentration of water vapor is much smaller in the mid-latitudes than in the tropics, that the gross moist stability will be much higher, and so the triangle will be mostly shifted towards the right side of the triangle most of the time. Although maybe in the summertime, who knows? And maybe in the summertime when it's humid and more warm, you can see stuff in the middle. But definitely because it's drier, it's not going to be.
That's why I was thinking, because one of these numbers is related to the balance in the momentum equation, right? In Y, and in X is the balance in the thermodynamic. So, but in the moisture, in the mid-latitude, when you have a low amount of moisture, you're looking at the right hand side of this diagram. Is that a right way to understand this?
Yes, that's right. That's correct. Yeah.
Okay.
Where in the tropics, you can actually get the whole triangle happening.
Right. I got it. Thank you.
And we have one last question from Tom Buechler before we close.
Sure thing.
Thanks for a great talk, Angel. I thought it was really pedagogical and I really enjoyed it.
Great.
So this may be nitpicking, and you just talked about the car frame versus the details, but I was very curious because a lot of your framework, especially for free tropospheric tropical dynamics, relies on WTG. And I mean, internal gravity waves are buoyancy waves. So some people have said it should be weak buoyancy gradient, but I'm guessing you use WTG for a reason. So do you think it's more convenient for how you close the equations, or is it the historical reasons, or what's your vision on weak buoyancy versus weak temperature gradient?
Okay. So the main reason why I'm just using WTG instead of something else is historical, but also pedagogical. Like it's pretty easy to explain, just temperature, and like the gravity waves and the emergence from it. From a practical point of view, I think, like whatever, leads to less error, is probably like the best way to go. So when push comes to shove and you apply it, weak pressure gradient, weak buoyancy gradient is probably the better approximation to use in practice. But I think pedagogic in terms of, teaching and like reaching out concepts to people, like I think WTG is pretty straightforward to discuss. So that's why I'm using WTG. It's pedagogical.
Well, that makes a lot of sense. I was curious if you had encountered a situation where WTG was actually better than weak pressure, weak buoyancy gradient.
Yeah, no, I like all the literature seems to suggest that maybe the one that, the one that can compete with these two that you mentioned is the spectral WTG, in which you vertically decompose into modes and then analyze those modes independently. That one seems to be pretty good, but the traditional WTG is definitely leads to a lot more error, and I wouldn't use it in comparison to weak pressure gradient, for example.
Okay, perfect. Thanks a lot.
Okay, well, thanks for a vibrant discussion and a great talk on health. Thanks again for coming to visit us, and goodbye, everyone.
All right. Thank you.